Okay, so I'm trying a new method of connect my iPad today. I hope you can all see the Boson-Hubbard model notes. And can you see my pointer there?
Yeah.
Yeah, okay. Okay, so welcome everyone. Let's get started then. So far we've talked about phases of bosons and fermions in the limit of weak interactions. At least there we think our theory is reliable. And for bosons, we found that weak interactions and low enough temperatures, boson just both condense into superfluid. And for fermions, they form a Fermi surface and a Fermi liquid. But at even lower temperatures, there's invariably some weak attractive interactions of the quasi-particles near the Fermi surface. And then the fermions pair into Cooper pairs, and then the Cooper pairs via the BCS theory give you a superconductor, which you can think of as condensation of Cooper pairs also. So we went through all of that and fundamental characteristics of these phases. And these phases could be present at strong interactions, but we then have no control. So today we want to start a more careful discussion of what happens at strong interactions, some new phases that appear at strong interactions. But before I start that, any questions on all the topics we've covered so far? Okay, I should also remind you, I put the second problem set on the website. These are problems on superconductivity that I've taken out of the book by Bruce and Flensburg. I've also copied a few pages from their chapter on Bruce and Flensburg. You really shouldn't need anything more than that and what's in the class notes, I think. So the second problem set is not due till the 30th. I think this I made a due a week after that, but he had a long time for the first problem set. Sorry, the first problem set is due on the 30th, and this would be due a week after that. And if you need more time, you can alert me to that. And of course, as always, you can discuss these problems in section or contact either of us anytime. Okay, so we want to look at new phases at strong coupling, strong interactions. The simplest context turns out to be look at bosons moving on a lattice. And the phases we're interested in is roughly phases that are not superfluid. They are phases that will have an energy cap that will cost a finite energy to create an excitations. And if these were electrons, you'd call them an insulator if they were on a lattice. You can also talk about models on the continuum. They're a bit harder, but in the end, they don't really give you any fundamentally new insight. So we're going to stick to the simplest context of bosons being on a lattice. Okay. So right. So there are these notes here, which I've written some years ago, which I was just rereading. I think I'm basically going to just go over what's here and draw a few pictures. So you should have a lattice with sites I, and there's a Bose operator on each site, which obeys the canonical Bose commutation relation. And then you also define the number of bosons to be B dagger B as usual on each site. And so we are going to work in the Gantt canonical ensemble. And so this number, can we take any integer, any integer which is greater than or equal to 0. Its eigenvalues are integers, and so the set of all non-negative integers on the square lattice tells you, which are denoted by this curly MJ, gives you the set of all possible states of the system. Okay, so that's a very large set of infinite set of states there, because the MJ, even for a finite lattice, because mj can go all the way to infinity on a given site. And then on this Hilbert space, we're going to act on with the famous Bose-Hubbard model, which is right here. So this has got a hopping term, which we're now calling W for bosons being nearest neighbors. Previously, we called things like that T. That's another common notation. There's a chemical potential that couples to the total number of bosons. And there's a repulsion between the boson of magnitude U. And this is a pairwise interaction between the bosons. And that's why you have the NB times NB minus 1 over 2, because that's the number of pairs that you can make out of NB bosons on the site I. So it's completely on site. There's no interaction between the bosons which are not on the same site. So, and this also turns out to be a pretty good approximation, in fact, an extremely good approximation to bosonic ultracold atoms moving in an optical lattice. The next chapter will start thinking about what happens if there are interactions which are not completely on site, but with nearest neighbors or even longer. And that gives a much richer phase diagram with all kinds of interesting possibilities, which are going to occupy us for much of the remainder of the course. But today we just talk about the case where U is completely on site. Okay. Yeah. So now if you take the continuum limit of this, assuming that the bosons only occupy very long wavelength states, then you're basically back to the Bogoliubov Hamiltonian. This is just a lattice version of the Bogoliubov Hamiltonian. So in the case with the density of bosons, there's only a few bosons per lattice site, so the bosons are mostly moving over distances much larger than a lattice spacing. Then this is nothing but the Bogoliubov Hamiltonian. And so we studied the Bogoliubov Hamiltonian in the limit where U was small. So today we want to study the same Hamiltonian, but on a lattice in the limit where U goes to infinity. We want to come up with a treatment of this where U is very large. And hopefully we come up with a treatment which also works when U is small, but we want to treat the U goes to infinity limit exactly. Or alternatively, since the only relevant parameter is W over U, we want to treat the limit W goes to 0 also in an exact manner, and then look at what happens at non-zero W. So that's the exact opposite of what we did for the Bogoliubov theory. You first treated the free boson Hamiltonian, and then as an afterthought, you put some interactions. Now we're going to do the opposite. We're first going to think about this, and then turn on the interaction, as you'll see. So in keeping with that complementarity, what we did in the Bogoliubov theory was we treated this term exactly. I mean, yeah, diagonalized it. It just became the bosons in momentum eigenstates. But we factorized this term. We took this term and started factorizing the B's. So today what we're going to do is exactly the opposite. We'll treat this exactly, and we're going to factorize this term, curiously. And that will turn out to be the technique that gives us some understanding of what happens at large U, not just small U. Okay. All right. So here, okay, before I get to that, let me also note that this system conserves number of bosons, and you may know from Noether's theorem, there's a symmetry of every model that is related to every conservation law. So here there's a symmetry of B goes to B to the I phi, and the conservation law associated with that, where phi is the same on every site. Only then this is change a variable that does not change the Hamiltonian. The consequence of that is that the total number of bosons commutes with the Hamiltonian. So yeah, in B commutator H. Oops. 0. Okay. Okay. So, all right. So what was I saying? Right. Okay. So what we're going to do, let me just tell you what's actually the simpler way to do what we're going to do today, which is just follow the tricks we learned for weak coupling and just apply them to this model. And the trick we learned at weak coupling, or really it was an assertion at some point, was that you can just factorize many particle terms into simpler terms that are lower order by replacing some of the operators by expectation values. So if I do that here, that's relatively simple, and in fact, you'll get the right theory. But today I want to do a little bit better because this is such a simple model. You can actually make progress by doing a more careful calculation. And the more careful approach will be a variational approach. We're actually going to just say, okay, we're going to do a very canonical variational calculation. And then we have some variational parameters, which we'll minimize and see what happens. And that turns out in the end to this factorization procedure to be completely equivalent. But let me first tell you what the quick and dirty method would be. So the quick and dirty method would be to just take this Hamiltonian. So you had the Boson term, which was U n times n minus 1. Why is my... Well, this you just leave it the way it is. U n times n minus 1. And the hopping term was minus W B dagger I Bj plus the for a given bond, nearest neighbor bond, B dagger J Bi. So by the factorization trick, what we would say is that we just replace this by minus W B dagger I times expectation value of Bj plus all the other things that I can write down, plus expectation value of B dagger I Bj, and the same for the complex conjugate there, plus B dagger J, expectation value of Bi, plus expectation value of B dagger J times Bi. So I've just willy-nilly just replaced at least one of the Bose operators by an average value. So this gives you this by the factorization rules. There's an overall constant, which I won't worry about. Okay, and now I assume that this expectation value is the same on every side. So I just assume Bj is equal to some number psi, complex number psi, not to be confused with the field operator, which is the same on every side. I guess, what did I call it? I think I called it psi sub B. Okay, you can fix that later. All right, if you do this, so what you then see is that what you get the same Hamiltonian on every side. So what you get is minus sum on I. You get on each side Z times B dagger I times psi plus Z times psi star times Bi, where Z is equal to the number of nearest neighbors, number of neighbors. Oh, sorry, what's going on here? This is Siri acting up, excuse me. Okay, I don't know why I started Siri there. Number of nearest neighbors. Okay, that's because for every, so the sum over J here, sum over nearest neighbors Ij. Why is this acting up today? Okay. Yeah, the sum over nearest neighbors. And And therefore, the number of sum over j will give you a factor of z, where z is the number of neighbors. Okay. All right. So that's what you get if you apply the factorization rule. Now this, okay, so now we go back to the original term where I neglected to say this was a sum over I, and there's an ni here, and so this is a very complicated term with lots of Bose operators in it, and we said we're not going to touch it. So how are we going to treat it? It seems really hard to treat, but now we notice something when we do this factorization, that the Hamiltonian has split into terms which are only on a single site. So every term here only involves a single site, and every term over here only involves a single site, and every term here also only involves a single site. So our Hamiltonian, the full Hamiltonian, is of the form sum on I, H sub I. So if you want to diagonalize this Hamiltonian, life is simple. I can ignore all the other site and just solve the Hamiltonian on a single site. And that, that's not so bad, even because I have all these interaction terms. You can put it on a little computer, or you can do some expansions in powers of psi. You can pretty much figure out almost everything about it. And so that's the trick. So we can now solve this Hamiltonian for a fixed psi, and then we do the self-consistency as you do with any kind of mean field treatment, where you solve this equation in the end, and then that gives you the value of psi. So everything I'm going to say the next half hour is just exactly that calculation, but done in a different way. Okay, so let's go ahead and do it the different way. So the different idea is, as I said, a variational calculation. I guess I called it psi sub b. So let me just quickly change that. This is psi sub b here. Okay. So the idea here is to do something variationally. So normally, when you first meet a variational calculation, you say, give me a wave function. And then I vary the wave function with respect to some parameters. And then I minimize the energy of the original Hamiltonian. Now, in a many-body system, it's hard to write down a wave function. So what I'm going to give you is not a wave function. I'm going to give you some other Hamiltonian that I like, some simple Hamiltonian, which I've chosen to call HMF, or H mean field. So this is a Hamiltonian I can cook up. I can take any Hamiltonian I want. So I'm going to take a Hamiltonian, which is in fact precisely the factorized Hamiltonian we saw above, which has a special feature that the different sites are completely decoupled. So this Hamiltonian is also of the form sum on I of some H. And this Hamiltonian depends on parameters. In this case, the parameters are psi b star and psi b, which I don't know. So my assertion now is following. I pick a Hamiltonian, simple enough that I can figure out its ground state. And this is almost true for this thing. So I figured out the ground state of this Hamiltonian, whatever it is, and that ground state is my variational wave function. And then I minimize the expectation value of the true Hamiltonian with respect to the ground state of the fake Hamiltonian, the mean field Hamiltonian. Now the wave function will depend on psi b. And so then I keep varying psi b as much as I want until the energy of the true Hamiltonian is small as possible. That's the variational principle. So, so this approach has the nice feature that you're guaranteed to get energies that are bounded from below. If your Hamiltonian makes any sense, there's got to be some ground state energy, and there's no way your expectation value is going to go below that energy. So it's has all the good, comfortable features that you have in variational calculations. The only difference is that instead of specifying the wave function, I specify a Hamiltonian because it's easier to work with Hamiltonians in many-body theory, which depends on some parameters. Really, that's all. So that those parameters will be this one complex number, which I take to be the same on every site. So I have just one complex number, which is basically the Bose condensate amplitude on that site, expectation value of BI. Okay, so that's the procedure, and now let's just implement it. Now it's just a technical procedure. How to implement this is do the calculations. You can put it on a computer if you wish. Pick a psi, find the ground state of H mean field, minimize the energy of the true Hamiltonian in that state. Okay, so that's in fact the correct way of stating what mean field theory is all about. And everything we've done so far with the BCS theory and the Bogoliubov theory could be rephrased in that language. Part of the reason I didn't do it that way to begin with, well, first, it's a little more cumbersome, but second, this approach is great in that it gives you, it's unbounded it's bounded from below. It's always guaranteed to give you an answer, but it's very hard to improve it. That is, we can't talk about fluctuations and corrections about the mean field theory. Whereas the other approach, the factorization approach, and more precisely the Hubbard-Stranovic approach, allows you to improve things to any order you want, depending on how hard you're willing to work. Here, it's really hard to go beyond the first answer. So if you don't get the answer right to begin with, the variational approach may not be the best approach. Okay. Right. So this is what we're going to go through. All right. So then you can work out the following result, that the energy that you have to minimize is this one. Okay. So let me show you how we got that. Yeah. So I'll make another page here. Where are we? Here, right? Oops. Okay. Okay, so we have some mean field Hamiltonian. Oops. Right. So I have a mean field Hamiltonian. And presume I figured out its ground state. So that's my G, which is it's chosen so that I can figure out both G and EMF. These are numbers I can calculate because it's a very simple Hamiltonian and sum of Hamiltonian on each side. The sides are independent of each other. Okay, so now I have my true Hamiltonian. And what I want to evaluate is the expectation value of the true Hamiltonian in this ground state and minimize this. Well, often it turns out to be useful to write this in the following sense, in the following way. It turns out to be, oops, because that your mean field Hamiltonian and the true Hamiltonian are not that different from each other. So it makes sense to, why is this not writing? Yeah, okay. To take the expectation value of H minus H mean field, and then add the E mean field over here. This is obviously true if you just work it out, because the G is an eigenstate of HMF. And so you only need to take the difference between the two Hamiltonians and look at the expectation value, and then write down add EMF. Now, in our case, that makes life very simple, because if you notice our mean field Hamiltonian here, it has the feature that all of these terms, the complicated terms in the interactions, are the same between mean field and the exact Hamiltonian. So the only expectation values H minus H mean field have to do with the difference of these with the hopping term. And now for the hopping terms, another very nice thing happens. And this is also exact for this mean field Hamiltonian. So the hopping term that you do have to worry about, it's sum over ij, nearest neighbors. I'll just pick one of the terms. It's minus W times. So we have to take the expectation value on G of B dagger I G B of G Bj. Oops, sorry, I already wrote the answer before writing down the form correct expression. So this is the expression you originally get, Bjg. And now the point is that the wave function G is a very special type of wave function. It's product on I of a state on every site, because the Hamiltonian is the sum of Hamiltonian on every site. So the wave function actually factorizes between different sites. And therefore, it's an exact statement that this is equal to G B dagger I, G, and then G B J G. Because G is factorized between different sites, so you can just factorize the expectation value too. Easy to see once you use this form that this is true. And then these things we know are the same on every site. So basically, this you can you can even drop the i's, and this doesn't matter because it doesn't matter which site you're on. Then you do the sum over ij, and it just gives you what the answer is. So if you apply that trick, then you get this expression here. So here, this is a system of m sites. So I'm looking at the energy per site. So energy per site is the energy of the mean field energy divided by the number of sites. This is the term I just showed you, expectation value of B dagger B. That's present in the original Hamiltonian. And these are the terms you have to cancel out because there were terms in the new Hamiltonian that were not present in the original Hamiltonian. Okay. So basically I've reduced everything to the following problem. You only need to worry about one site. So you just pick a site, let's say the site 0, where you have this Hamiltonian, which is right this here. And let's say either on the computer or whatever methods, you can find its ground state. Okay, you can find its ground state, and you can also evaluate expectation values of any operator. So you know all of that. And therefore, you go ahead and evaluate the expectation value of B, B dagger expectation value of the complex conjugate, and you insert that in here. You insert the expectation value in these numbers. You also know the ground state energy, and everything depends on psi. So now there's your function. All that you have is some function of psi. It's just a complex number, and you minimize it. That's it. Okay, so to minimize this, you have to take the derivative of this with respect to psi. And at that point also, there's another very useful result that you can use, which is the following. This is sometimes called the Feynman-Hellmann theorem, but very easy to prove, and I leave it as a homework problem or for discussion in section. So you have some E mean field, which is the expectation value of the Hamiltonian, or the ground state energy of the Hamiltonian, which is a function of psi. And you have to evaluate d by d psi of this. Well, it turns out this is very easy. This is the same as evaluating the expectation value of dH mean field d psi. And so this is not immediately obvious because E mean field of psi is equal to psi h psi. And so when you take the derivative, sorry, not psi, it's G. Why did I write psi again? It's GH psi, GHG. And this should be G, sorry, excuse me. Yes, no, that's correct. So when you take this derivative, you'd have to take the derivative of G and the derivative of H and derivative of this G. Turns out the first and the last derivative cancel with each other, and you only have to take the explicit derivative. The other derivative is not necessary. So this is an important trick that you can verify, which I won't verify now. Just use the orthogonality of the eigenstates and you can prove it. Okay, now what is this? Well, this is easy. What is DEMF d psi? Well, that we know from the form of HMF, which is right here. So DHMF d psi, well, it's just B dagger minus B dagger right there. And you just have to take its expectation value. So so this thing becomes here. So the whole thing is equal to minus. So this is a expectation value of B dagger in the ground state. And then you also get a psi from the Hamiltonian. So that's what it is. So basically, you have to take the derivative of every term in here by this trick. Keep using that trick over and over again. And you can also take, yeah. So when you work this out carefully, it's a little bit more cumbersome, which is why I didn't do this. At the end of the day, when the dust settles, you get this equation. That the expectation value of psi is just z times w times b. Okay, there's a slightly change in notation from my mean field calculation here. When I did this mean field calculation, I think I called psi something else. Okay, but if you just modulo that change in notation, so let me not call this psi sub b, it was a different psi, up to some factors of z and w. So if you just compare, okay, now I forgot the factor of w here. There should be a w here. Yeah, if you just look at what we got here by the quick and dirty method, that's exactly equivalent to this variational calculation. If we did everything carefully, and it was more cumbersome, so this is something I just want to show you once, so that from now on, you just go ahead and do artifact and factorize everything without worrying too much. But if somebody really asks you, how do I know this is a good thing to do, you can point to a variational calculation like this, and then prove it that it's a variational estimate for a certain free energy functional. Okay, so that's the procedure. It's still required. It's still not that easy to work out, because this Hamiltonian, this mean field Hamiltonian here, is not so easy to diagonalize. And the reason it's not so easy to diagonalize, so even on a single site, the number of states here is infinite, because you can put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bosons on a site. So what you do, but of course, the more and more boson you put, the energy cost goes up and up, because the bosons repel each other. So you just put on a computer and maybe 10 bosons and look at the ground state, then put 11, then put 12. Pretty soon you'll find it doesn't make much change. So it's very easy to get the answer to any accuracy you want. It's just a single site problem after all. It's effectively a nonlinear harmonic oscillator. Not so hard to work out on the computer. But let's try to do at least a few things analytically. So what we can already see without too much work is that there's a regime that once psi b is non-zero. Suppose I solve this equation. I minimize this energy, and I find that psi b is non-zero. Once psi b is non-zero, that means I have a Bose condensate, because psi b at the saddle point is equal to expectation value of this operator. So once this is non-zero, I have a Bose condensate, which immediately sees I have a superfluid. So I have worked very hard, but essentially got something that's almost the same as the Bogoliubov theory. So the question I really want to ask here is there ever a regime where psi b is zero? And this is going to be something different. So I'd have a state of bosons where there's no condensate at zero temperature. Is there such a regime? And the answer, of course, is yes. So let's just put psi b equal to 0, and then try to turn on a non-zero psi b and see what happens. All right. So now when I put psi b equal to 0 in the mean field Hamiltonian, life is very simple. I can give you all the energy eigenvalues. It's really if this term is 0, so at psi b equals 0, this Hamiltonian, even though it's nonlinear in terms of the Bose operator, is a classical Hamiltonian because NB only involves a number operator which commutes with itself. Okay, so there's nothing to do except remember that the number is an integer. So therefore, I know all the eigenvalues of H mean field, and here they are. Where are they? Yeah, so they just labeled by a non-negative integer mi, which we are going to call n0 of mu over u, because we'll see. And so these are all the eigenstates for any integer. And then we can, so you could have 5 bosons, 3 bosons, 5, and the energy eigenvalue of these eigenstates. So E of mi, if you pick an integer on site I, which is mi, will be minus mu mi plus u times mi times mi minus 1 over 2. So I have a very simple task now, is find the integer for which this energy is as small as possible. The key thing, really crucial from other minimizations you've done before, is that mi must be an integer. That's where the quantumness is coming in. Mi has to be an integer. It's not a real number. We have been minimizing something with respect to integers, which is not something we've done so far. So, but that's a simple problem. Just figure out as a function of mu over u what integer minimizes its energy. Okay, and so here's the answer, and that integer we'll call n0. So for when mu is negative, the best integer is 0. When mu is between 0 and mu, it's 1, and so on. So there's these integer steps, and there's a phase diagram here, which now I'll refer to. So and also, I guess it goes without saying, where's the diagram? That this procedure is exact when there's no hopping, when W is 0. It's also exact when psi is 0. So, there's two ways to make psi 0. You could put W equal to 0, or you can make B equal to 0. Either way, this works. So let's just think of it in terms of W equals 0 for the moment in this respect to this phase diagram. So you're on this axis. So on this axis, as you raise the chemical potential, when the chemical potential is negative, the world is empty. There's nothing in the lattice. And here, when mu is between this region and this regime, you have exactly one boson on every side. So basically, if I were to draw the lattice, here's my lattice. I have exact square lattice. I have one boson on every side. And that is the exact ground state here. Okay. And then in this regime here, you have 2 bosons on every side, and so on. So the minimum is at 2. So I don't know if I can draw 2 very well. Let me try to pick another color or something. So I have 2 bosons here, and 2 bosons there, and 2 bosons there, and so on. Okay. And those are the eigenstates when there's no hopping. This integer, the number of bosons per site in the grand canonical ensembles, it jumps from 1 to 2 to 3 to 4 to all the way as you keep increasing the chemical potential, or if you wish, increasing the pressure from the environment, and more bosons enter. So for a while, one boson will enter, and then you'll try to put more, but the bosons that are already there will repel them all. Then you try to push them more and more, and suddenly all 2 will enter. So you get this jump in the density as you go up from 1 per site to 2 per site, and so on. And that's very much due to the discreteness of the boson number, that things happen this way. All right. So now let's just keep W finite, but small. Okay, so now the question we want to ask, is this state stable? That is psi, even for non-zero W, is it still the case that the energy is at psi equals 0. Okay, so to do that, and in fact, for a while, I'll prove to you that. I mean, I'll give you the argument in a minute. Before that, let me make another statement about the state. This phase diagram here. Where did it go? Yeah. In fact, it turns out that for small w, and I'll just write down the answer here, and we can look at the answer for large w. So for w small, for w much smaller than u, if you compute the mean field energy as a function of the psi, that turns out to be r times psi squared plus higher order terms, and r is greater than 0. So this means that provided w is small, so let's say we're somewhere over here, then our psi will remain 0, at least in mean field theory. Okay. So the Bose condensate won't immediately appear. In a while, we'll figure out where psi first becomes non-zero. Well, it becomes non-zero on this line here, obviously, and this line is determined by putting r equals 0, and we'll figure out how to compute that in a minute. Okay, but for now, let's just imagine that we are somewhere here. So at 0 hopping, there was 1 boson per site. Okay, so now I turn on some hopping. Okay, now once I turn on hopping, I'm going to get, now let's go beyond mean field. I'm going to make an exact statement, which is independent of anything, just uses an exact statement about this many-body Hamiltonian. It's not just, it's true in mean field, but in fact, it's true beyond mean field also. So what is the statement? So now once I turn on W, then my wave function will not just be this state. So now I'm going to go a little bit into this regime. So, I'm going to go somewhere here. And then my wave function, of course, one component of the wave function is this, but there'll be fluctuations. I'll also have in my exact wave function states like this. If I do perturbation theory in W, I'll get some sites that are empty, and this site will have 2 bosons. Maybe this will have 1, 1, 1, 1, 1, 1. So and then dot, 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 an infinite number of such terms, right? The bosons hop around for a while, and I get a very complicated wave function as I vary W. And the wave function will change, these fluctuations become larger and larger, and looks like life is hopeless. How can I possibly make any firm statement? But a firm statement you can make, and that statement is that everywhere in this regime, where you can just do perturbation theory starting from the Mott insulator, you have the property that the number of bosons n hat on every site is still exactly equal to 1. There's no corrections to this. That is, the density in this Mott insulator is 1, period, with no corrections on every side. Even though the wave function, you look at this wave function, if you sit on this side, you would say, well, here it's full, here's 1, and there it's 0. So there's some fluctuation in the number of bosons on that side. So maybe it's not exactly 1, but that's not true. In fact, it's exactly 1. Of course, the reason being that there'll be other fluctuation where there's 2 there and 3 there and 4 there, and they all have to exactly cancel each other out. And to give you an average value of 1. And why is that? Well, the reason behind it is twofold. One is that the total number of particles commutes to the Hamiltonian, the exact Hamiltonian. So because of that, whatever the value of n hat was at W equals 0, the total number of particles, it can't change. In any ordered perturbation theory, you're going to preserve the total number of particles. So that's point number 1. Point number 2 is that you still maintain translation invariance. So if the total number, so it's certainly true that the total number won't change. But if the average value has to be the same on every site, well, then the total number, the number any side is just 1 over m times n, and that also can't change either. And therefore, this is true. So that's the description of the Mott insulator. It has a fixed commensurate density of 1, 2, 3, or nothing else. It's an insulator. It does have, virtual fluctuations like this, which become larger and larger as you approach the boundary of the Mott insulator. But everywhere in this region, the density is fixed. This whole region, the density doesn't fluctuate. And similarly, there is 2 and 3 and 4 and 5. Okay. And another question we can ask now: what is the excitation energy? How much energy does it cost to create any excitations? And now it's very different from anything we have met before, like the superfluid or the Fermi liquid. It costs some energy to create an excitation, because the only way you can create an energy, as you can see, to say which conserves particle number, is this excitation I just showed you, where one particle from here hopped there. So here you had two particles. Let's look at these two sites. Their initial energy was E1 plus E1, because you had exactly one particle on that site. And now you have E2. The final energy is E2 plus E0. And you'll find that this is, if you take the difference of this, it's always greater than 0. Where E2, E0, E1 are just exactly these numbers I wrote down here. There. This is EI. So now I've changed notation again. This is same as our E sub m. So m is an integer on side I, and the excitation energy of creating this excitation is E2 plus E0 minus E1 minus 2E1. And in fact, so if you actually work out this energy as a function of mu, one second. So the gap has to vanish on this line, I believe. Yeah, okay. But the actual state, sorry, yeah, so that's not this is always positive, no doubt. But the actual excitations, now these particles and holes can actually lower their energy by moving around. So here I'm assuming the excitations are localized, but they're not. They move around in momentum eigenstates. So they can lower the energy more than this. And this boundary here is precisely the locus of points, which we'll compute in a minute, where the true excitation energy to create a particle-hole pair vanishes. Okay, and once that excitation energy vanishes, you go back into psi non-zero, as this shows, and that becomes a superfluid. All right, so the task before us, therefore, is to figure out how, figure out this number r, and then see where it vanishes, and that will give us this phase boundary. Where the Mott insulator gap vanishes, the gap to create any excitations at all, and then you get a superfluid. Any questions? All right, so now you have a task, which is again a bit cumbersome, but again the principle is very, very simple. I have an expression here for, where is it? For the ground state energy of the system as a function of this variational parameter psi. And everything here is a property of this Hamiltonian, which in general I can't diagonalize, but I can say that I can certainly diagonalize it, and I just did, for psi equals 0. So you just sit down and do perturbation theory. So you do perturbation theory in psi to figure out the first and second order corrections to the ground state energy and wave functions of this Hamiltonian. And then you plug that expression in here. And then you expand everything into second order in psi. Okay, that take you a few hours, but it's just a simple application of perturbation theory. So in principle, it can be done. I mean, it's a very well-defined procedure. You just do perturbation theory in psi for the Hamiltonian and its wave function, plug the results in here, and then you have a perturbation theory of your true Hamiltonian as a function of some parameter psi. Okay, so I actually went through that once, and you can have fun going through it at some point, but it's really an application of perturbation theory. And what you find then is this result. So this is what you get. So this is equal to, so the free energy or the energy E naught of the true system is some E00 we don't care about, plus R times psi squared, and R is equal to this, where chi naught is equal to this. And what is N naught here? Well, N naught is an integer, but depends on mu over u. And it's precisely the N naught of the Mott insulator. So it's a different integer for each Mott insulator. Here's the function. If you want a function, this is N naught is a function of mu over u, which is 0 for this range, 1, 2, 3, all the way for this range of values. Okay, so it's just some function of mu over u. All right, so there's the answer. That's the exact answer to order psi, bit of algebra. And you just plot this function as a function of w and find where r goes to 0. And that's how, in fact, I wrote a little program. That's how we got this curve. Okay, so what we find is that at a typical point, you have to, so here we have, in a sense, zero hopping, or conversely speaking, infinitely strong interactions. And then you increase the hopping, and it takes a while before the bosons decide to Bose condense. Before that, they're rigidly stuck in one of these insulators or solids, where you have exactly one boson per site. And here is 2 and 3 and so on. There's one exception here, right at these points. So if you look at these points, and these are points where at W equals 0, for example, here, the state with one boson and the state with two bosons have exactly the same energy. That just happens to be at when mu over u is equal to 1, then you'll find that this function, where did I write that function? Yeah, so this function, when u is equal to mu, has the property that it has the same value at m equals 1 and m equals 2. Okay, I'll let you figure that out, but that's, I'm pretty sure it's correct. Okay, so that works out. So what happens here at this point is that any given site can't decide whether it has one boson or two bosons. It doesn't care. It could be either 1 or 2. So there's lots of number fluctuations. There's no energy gap. You can put one boson or two. There's a degeneracy in the ground state, if you wish, on each site. So each site can be 1 or 2, and it can be anything. So if you allow some hopping, well, these bosons can move around no problem. There's nothing stopping them. There's no energy cost they have to pay, because ones can move into twos and twos can move into ones, and therefore it becomes immediately a superfluid. Okay, all right. So, and we should just try to figure out also what is the average density at this point. The density of bosons here at that point will be exactly halfway in between, no surprise. So exactly at this point, the average value of n on each side will be 3/2. And exactly at this point, the average value of n will be 1/2, and so on. And so in the Boson-Hubbard model, those points are very special, where you have exactly the boson density is exactly half filled, and you have some hopping, then they always become superfluid. The on-site interaction is never able to localize the boson into some integer density in this phase diagram. Okay. Okay. Questions?
Sorry,
So,
could you? Oh,
yeah, please.
could you just show the expression for chi for like one more minute?
Yeah, go ahead, please.
Thank you. No, I just wanted to write it down.
Yeah, well, these notes are on the website, so you don't really have to write it down. But yeah, we're going to actually, so this is actually a bit of a mess. But one, you do notice a simplification here, that when you're only interested in r equals 0, when is r equal to 0? It's just r equals 0. So this r equals 0 implies that chi naught is equal to 1 over zw, whereas this chi naught is this. And next time, we're going to derive this condition by the same method we used for the Landau-Ginzburg theory for superconductivity. Fermi liquid, we do the exact same type of calculation here by a Hubbard-Zadanovich transformation, and you'll get exactly this condition. And depending on your background, one or the other calculation is a lot easier. If you know a little bit about Green's function, then the Landau-Ginzburg calculation is much easier. If you just want to do perturbation theory, at the level of this on-site Hamiltonian, then this is the foolproof method. In fact, the method I've outlined today is truly, in a sense, foolproof, because you can apply it for any Hamiltonian and for any mean field Hamiltonian. You can pick anything you want, and then you can do perturbation theory in various parameters, and you're guaranteed to get at least an upper bound on the ground state energy. And so that's really all. And it turns out to be good enough in this problem. It need not be in other cases. So in the few minutes remaining, before I say more about the more path integral approach to this problem. So what we're going to now look at with the path integral approach, not right away, not today, is try to understand then these phase transitions, what happens across this boundary. As you cross from the superfluid to the insulator, how would you describe that? And that leads us to another new type of state that we haven't met yet. There'll be a quantum critical state, where there'll be strong quantum fluctuations at all length scales, and we'll say a bit about that, not too much for now. So these phase boundaries turn out to be exceptionally interesting in this Bose-Hubbard model. And a lot of that has also been investigated in many experiments now. But now let me make a few more remarks in a minute or two I have left. What happens here in a more general Hamiltonian? So let's imagine, notice that at there the average density is 1/2. Imagine that it wasn't really, we were not really dealing with a Hamiltonian that was just the Hubbard model. In the real world, there's always something beyond the Hubbard model. Where's my page? Okay. Okay. So imagine we had a Hamiltonian, which was the Hubbard model that we've just spent the whole lecture on. Plus I had some more nearest neighbors with some repulsive interaction, Ni and J. And V I'm going to take greater than 0. And let's say, this, you put a small v, it doesn't change the phase diagram very much that I just showed you. But where it does change things a lot is when your, say, boson density is, say, 0.5%. Okay, so here's our lattice. And we're going to put one boson on every 2 sites. Okay, and we want to do that in a way that gives me a chance of, so far in the Hubbard model, there's no way I can do that without the system just becoming an insulator or a superfluid. But suppose I am near half filling and V is greater than 0. So this means that to minimize the energy, I have to keep the bosons apart from being nearest neighbors. I should not allow any pair of sites to have a boson. If I could do that, then I would minimize the energy. And so, and in fact, the way you can do that, then you can see right away, is suppose I make a checkerboard pattern. So I put one boson on every other site in this checkerboard pattern. So this is also turns out to be an insulator for some regime of parameters at average density per site is 1/2. Okay, so I can get an insulator at 1/2, provided the hopping is small enough. And the reason is the same as before. Every time I want to move a boson, if I try to move this boson, it's going to run into a problem. When it runs here, it'd be repelled from these two by energy V. So there'll be an energy gap when V is positive. So roughly you might guess that as long as W is smaller than V, then this insulator works. You won't want to pay the price for this boson to hop there, and so that they'll remain rigidly. So it seems like you can get an insulator even at half filling, provided you have nearest neighbor interactions. But you paid a price here. You paid a price because this insulator is not unique. There's 2 of them. There's either the black squares or the white squares of the chessboard. So there's a broken symmetry. You have broken translational symmetry, some kind of Ising symmetry. You have 2 possible insulators at half filling. So that's, at least in these simple models, if V is not equal to 0, then the phase diagram will get a little bit modified. You don't, where's the phase diagram? Sorry. Yeah, so this famous phase diagram gets slightly modified, and you're going to get another lobe here with checkerboard order. Where it'll still be an insulator for a while with density 1/2, and so on. And you can see from this that if you put further and further neighbor interactions, you could get insulators at almost any rational number by tuning all the parameters. But you then do have the feature that the number of bosons in the new lattice. So when you get this checkerboard pattern, when you get this pattern, the new lattice has a unit cell of 2 sites. You can think of this as a unit cell now. And there's still an integer number of bosons per unit cell. So any insulator in this picture of broken symmetry must have an integer number per unit cell. Okay, we'll come to this. As we'll see, that's not exactly right. And that's really, that it's possible to get more exotic insulators, which then start looking like, many, which have topological order, even at filling that's without an integer number of bosons per unit cell. That will be the next chapter where we start some really modern topics. But in terms of these kind of Hartree-Fock calculations, you have this feature that there's always an integer number of bosons per unit cell, and depending on your filling, that may require you to break a symmetry or not. So if you have exactly 1 boson per cell, you don't have to break a symmetry. But if you have half a number of bosons per site, then you have to double the unit cell and so on. So if your density is P over Q, the ground state of your insulator must have a unit cell of at least Q sites. Okay, I'm getting that. That's giving you a taste of some of the questions we're going to look at. All right, I'll stop there. I've already gone over. Questions?
So this might be super simple, but like you have this order parameter that's like psi here, And then you have
Yeah.
the phase in the superfluid. Are they linked in any way, or like they seem like complementary in some sense? But like, are they linked, or is this the wrong way of thinking?
Oh yeah, absolutely. They're the same, apart from some normalization factors, and they are linked by this this saddle point condition. So when you minimize the free energy, you solve the equation dE. So this was a variational parameter, dE d psi equals 0. You find when you work through when the dust settles, gives you this equation. So this links your variational parameter psi with the expectation value of the Bose-Hubbard, and this is precisely the Bose condensate. Okay, so expectation value B is the 0. It's the same on every side, so it's a 0 momentum condensate. That's the number of particles in the condensate. This is equal to square root of NV of, or N0 was what we called it, the number of particles in the condensate. Yeah, so that gives you the connection between your variational parameter psi and the super. So once the variation parameter is non-zero, this implies that this is non-zero and so it's superfluid for all the reasons we discussed so far. You've broken the U1 symmetry. Another way to say it, this expectation value breaks the symmetry here, which associated with number conservation. This symmetry has been broken, and then that in turn implies that there is a phase variable which has a stiffness and so on.
And the other question I have is, the lobes get smaller as you go higher in the phase diagram?
Yes. So you have a guess as to why it happens. Somebody has a guess. That's due to also some very interesting physics. Don't do the calculation, just try to make a guess. So what's happening here? Okay, let me just try to give you a hint. So if I'm here, and in this Mott insulator 1, like I said, I have the bosons hopping around. So one boson, so here I have the process that gives me fluctuations, is I have 1, 1 going to 2, 0, okay? But let's go over here. Here you have 3, 3 going to 4, 2, okay? So that's the process you're looking at in perturbation theory, okay? So what is the matrix element for this process? So the matrix element, the process is if you have, let's say you have n on one side, let's call the sides 1 and 2. If you have n1 on one side, n2 on one side, then you have an operator which is going to create a boson on site 1 and highlight a boson on site 2. So this state has to be n1 minus 1, n2 plus 1. So this is the matrix element, and there's a factor W here. This is the hopping matrix element, okay? Now, if you go back to your very first equation you learned in undergraduate quantum mechanics, this is equal to W times square root of N1, N2, okay? This is sometimes called the Bose enhancement factor. This is simply coming from the fact that A acting on N is square root of N times N minus 1. Is that correct? Yeah. Or B, this is the harmonic oscillator matrix elements are square root of N and square root of N plus 1. So you get this factor here. So effectively, this means that the hopping matrix element for this process is enhanced by this factor. So your W becomes a bit larger. It's getting square root of N enhancement. It's much larger than it is here. So the bosons are able to hop more easily when there's many of them, because basically because the wave function has to be fully symmetric, and you get this extra factor of square root of N. So because these are bosons, they hop much more easily. The matrix element for hopping goes up, and that's why the Mott insulators shrink. So if you have too many bosons per site, what's the difference between N and N plus 1 when N is 10? You won't notice it. In fact, they very easily fluctuate as a large matrix element, and it'll just be a superfluid. So that's the reason these shrink, because of this famous square root of N matrix element of harmonic oscillators. So also called the Bose enhancement factor in this context. This Bose enhancement factor, I think, is built into this calculation of chi naught. If you go through that calculation, I think it, I think that's the reason, in fact, you get these n naught plus 1 and n naught in the numerator. This is like an energy denominator. These things in the numerator come from the matrix element. These are the Bose enhancement factors.
Subir, I have a question.
Sure.
So previously, when we learned about like weakly interacting Bose gas, we do the Bogoliubov transformation, and basically we don't get a Mott insulator. Is it because we there's no like lattice side concepts there?
Yeah, I mean, if you're starting from the other end there, the previous theory. I don't know where this. Sorry, I should really have a separate. Yeah, the Bogoliubov theory was starting from here and we were coming this way. We were out at infinity here, and we did a perturbation theory this way. Now we're starting completely the opposite limit, where u is infinity, and then going this way. The Bogoliubov theory went the other way. So it simply doesn't know this. You're in the continuum. You don't know anything about the lattice. Now you could imagine putting a lattice potential here and then seeing what happens in the presence of a lattice potential. Yeah, but you won't see that in any order in perturbation theory. But as we'll see in one dimension, in Lattice liquid theory, even there is a way to see the appearance of these Mott insulators, even starting from the analog of the Bogoliubov theory. But that's special to 1D.
I'm wondering, like, if I'm understanding correctly, Bogoliubov transformation doesn't make approximations. It's like a change of basis to diagonalize the Hamiltonian. So in that scenario, even if I have the interaction very, very, very large taken to infinity, I don't think we have a Mott insulator, right?
Well, but so let's first of all imagine we are working, Hamiltonian, which has a periodic potential. So there's even the chance of getting a Mott insulator. But I agree.
Okay.
Now the Bogoliubov Hamiltonian, however, is not the full Hamiltonian. The Bogoliubov Hamiltonian is obtained by factorizing the original Hamiltonian and throwing out all b to the fourth terms. We did a quadratic truncation of the Hamiltonian. That's the suspect step. We threw out all the b to the fourth terms, and we have to put those back in and treat them exactly. And you notice over here, the b to the fourth term were treated exactly because they were part of the Hubbard interaction, which we treated diagonalized exactly.
I see. Thanks.
Yeah. So all those b to the fourth terms you throw out, you can't throw out. You have to treat them exactly. But any order in perturbation theory, at least in 2 dimensions and higher, you will never see an instability of the Bogoliubov theory. 1D is special because of Lattice liquid features where you can see this. And we'll come to that.
I also have a question.
Go ahead, Ning.
You taught this variational method, like the mean field, like writing down a mean field Hamiltonian. It's more like a guess, right?
Yeah.
Then is
Absolutely.
it guaranteed that
guess.
the ground state energy will be larger than the real Hamiltonian ground state?
That's guaranteed. That's just the variational principle. Works for many body or single body. That for any wave function, the expectation of the Hamiltonian is bigger than the ground state energy, the true Hamiltonian. So you have to distinguish 2 things. No. You have to distinguish 2 things. Here's my guess Hamiltonian. So my guess Hamiltonian can be anything, and this guess Hamiltonian has some ground state energy. That ground state energy is this. That can be, who knows what that number is. But this E naught is not the ground state energy of the guess Hamiltonian. E naught is the expectation value of the energy of the true Hamiltonian in the ground state of the fake Hamiltonian. And this whole thing is guaranteed to be an upper bound to the true ground state energy. That's the statement.
Oh, I see. Thanks. Yeah, that's all. Thanks.
Because the variational principle doesn't care what wave function you pick. So we just pick a wave function which is just the eigenstate of a fake Hamiltonian. That's all. But we have to make sure we work with the true Hamiltonian in evaluating the expectation value. That's what we did.
Oh, might I ask something?
Yes, Juven.
Super. I actually
please,
post on
go
the
ahead.
chat. It's really basic. First, why do we just make sure the Hubbard repulsion? Why do we write n times n minus 1 instead of just n squared? These are very beginning. I think I asked in the chat, but then it's not. It's very basic.
Well, because it doesn't.
Is that just for
here,
convenience?
No, it's very important. It's important for the whole numbers that I put in. It's because there's no self-interaction. You have a bosons can only repel some other boson. So if I have two bosons, I have it's 2 times 1. I mean, sorry. Yeah. So and there's a factor 1/2, so I just get 1 repulsion. If I have 3 bosons, I have 3 choose 2, which is so this combination here is just n choose.
So you count the channel of the repulsion between different bosons.
It's just
you
pairwise interaction. How many?
No problem.
I wouldn't say it's nothing fancy. This is just interaction. Every boson has to interact with some other boson. It doesn't interact with itself. With fermion, you don't worry about this because of the exclusion principle. You can never put more than 1 fermion in the same state, so you don't have to worry about this. But for bosons, you do.
But does it make sense to study for the n squared repulsion, or it doesn't?
I mean, okay. Formally, if you drop the -1, that shifts your chemical potential by some number. Okay, so your definition of mu will change, but this is the correct definition if you ever want to talk to an experimentalist. You have to put the -1 there.
No problem. Thank you. You also draw this phase boundaries. I wonder whether those curves are in the same universality class, or they could be different. They are gapping space, I suppose, the phase transitions.
Well, we'll come to that on Friday.
Okay.
The answer is yes, they're in the same universality class, but yes, their positions move because of the Bose-enhancement factors, but beyond that, the answer is yes.
And how is this picture generalized to or applied to higher dimensions? I think you are mostly focused on 2D space.
It's the same in any dimension. So far, this mean field theory doesn't care what dimension. If this picture applies, it's in fact basically correct even in 1 dimension. From 1 to infinity, it's fine. There are some singularities right at the tip here, which are different in different dimensions. Other than that, it's all the same.
Thank you.
I have a question. So when the boson number is restricted, so you cannot exceed the number, say a naught. So what will happen? It seems to me that the phase diagram only decreased by amount, but actually when you go down to the hard boson case, well, the whole diagram was basically changed.
Yeah, I mean, if you don't allow more than 3 bosons, you just stop the phase diagram here and so on. There'll be nothing beyond. I mean, well, yeah, I mean, those states are just not allowed when mu becomes, well, okay. So what happens to make mu really large and you can't put more than 3 bosons? Well, you just fill up. You just form a Mott insulator with exactly 3 bosons everywhere, or something like that. Yeah. I think this line would still keep going forever, and everything here will be Mi3, something like that. That thing won't come back. So at this point, the density of bosons is 3, and it'll just continue like this. And so the whole Mott insulator region will become very big if you don't allow more than 3 bosons per site, and so on. Yeah. So the phase boundaries will shift around, of course.
So how about we go to the hard boson case when you add the occupation number is only 0 or 1.
Yeah. Right.
So
So then, yeah, then the phase boundary will be something like this, and above this green, well, I don't want to. Hopefully, above this green line, you'll just have one boson per site. It'll be just a rigid, fully filled lattice. And then down here, you may have other phases.
got it. Thank you.
I mean, the mean field calculation that I've written down can be done for any, you can include that in the mean field with no problem. You just change your change the on-site Hamiltonian. All the things you're talking about are changes to the on-site Hamiltonian. So the point is, this could be any polynomial or any function of the n. The whole calculation still goes through. So you could just take any function you want here, and you can do exactly this calculation to figure out all the phase boundaries. Nothing will, the equation for R will change, but the same procedure will work. This doesn't have to stop at fourth order. It can go to infinite order. The calculation is as easy or as difficult, because diagonalizing this Hamiltonian was trivial. You just picked n to be an integer, that's all.
I have a question. Sorry, my internet is being quite weird. But in the 1/2 case occupation number, where we have the checkered
Yes.
filling, if we have a domain wall
Yeah.
between two different like checkered states, would there be some conduction along that domain?
Sure. Yeah, you can get some interesting behavior at these domain walls. Yeah. I don't know. Some people, I don't know if it'd be a superfluid along the domain wall. That will depend on some details, but there could be, yes. Yeah.
Okay.
Yeah. So you could get all these conducting channels in the domain walls, right? Yeah. Yeah, but you would have to just sit down and really look at the structure of a domain wall to properly answer that, depending on exactly what kind of pattern you have in your insulator. Yeah.
Got it. Thank you.
Yeah.
Excuse me.
Yes, Joan.
Yes. In today's lecture, conceptually, we didn't discuss anything about vortex, right? Does this still help for something, or it doesn't help? It doesn't help for whatever we need for superfluid to insulate.
Well, there's no difference from our discussion from last time. I mean, the vortex, of course, only makes sense in the superfluid phase. So you have to be somewhere here to see a vortex. But the general theory of the vortex will be pretty similar here, except you'll have to account for this lattice potential, which just, okay, that makes your equations more complicated to solve, but the general idea will be pretty much the same. You'll still have flux quantization and everything. That won't change. That doesn't require only requires gauge invariance, which is still true in the lattice.
I still have a question. So
Yes.
basically, we deal with the case of square lattice. So I wonder if we change into other lattice, like a triangular lattice or parallel lattice, well, the physics change.
Details could change, but the level of the mean field theory won't. If you take this mean field theory for a Bravais lattice anyway, the only place the lattice appears is in the value of z. All you need is the coordination number, and everything else is the same. So in this mean field level, at this level of this variational calculation, you get the same answers, except the value of z will change. But of course, there are corrections to mean field. Mean field is not exact. And all of those corrections will then depend in detail on the lattice structure. Yeah. But
yeah, I know that. Okay, I know that. Well, if we are in the parallel lattice and we assume the boson is hardcore boson, So in this way, basically we get some quantum spin ice and there will be new phase of state.
Well, that's not for the Hubbard model, right? Okay, that's a hardcore boson, right?
Yeah.
Nearest neighbor interaction. So we haven't talked about nearest neighbor interaction. So the quantum spin ice is some sort of analog of the checkerboard where, because of some special frustration, instead of having 2 states, you have an infinite number of states, which are insulating. Yeah. Okay, where'd that go? Where's my checkerboard picture? Sorry, I keep going back and forth. Here's my checkerboard picture. Right, so it's the analog of this checkerboard, but in a more complicated situation. Yeah. I mean, this checkerboard you can also write down for hardcore bosons where you don't have never allow 2 bosons per site. No problem. This also would work. But sorry, that's the classical spin ice. Quantum spin ice, okay, that's more like a spin liquid, and that's also possible here on the square lattice. And that's in fact the next chapter when we talk about the Z2 spin liquid, and that's a remarkable state of bosons at half filling, say on the square lattice, where you get an insulator but no broken symmetry.
But I think in 2D they are confined.
For the U1 case, not for the Z2 case.
Oh, okay, yes, for U1 case.
Okay, for those of you who didn't understand the remark, don't worry about it. This confinement, deconfinement, different gauge groups, you're going to hear about it a great deal in a week or 2 and for the rest of the course.
Sir, I think I have a related question. Maybe not, maybe you'll discuss this later, but what determines the phase boundary of the checkerboard region in the phase diagram?
Well, as I said, here's, at least qualitatively, here's the very crude estimate of where the phase boundary is. So imagine a boson hops from here to there, okay? If it pops there, it has to pay an energy, well, let's say V here, V here, V here, like 3V. Okay, so let me put a factor of 3 there. So it pays an energy 3V to hop there. On the other hand, it gains an energy W. So now you might say, okay, if 3V is bigger than W, you don't want to pay the price and you'll be an insulator. But if 3V is less than W, you may as well pay the price and start moving around, and then you become a superfluid. So this would be a very naive guess as to where the phase boundary is.
Right, okay, thanks.
Okay. But to do that better, you have to do a mean field theory. But now life becomes a bit more complicated because now you have some interaction terms, but it's not that much more complicated. You have some interaction terms that are off-site, but they're still diagonal in the end. So your whole mean field procedure becomes more complex. It's the procedure I've outlined you can still implement as a variational calculation. It's just the calculations are a little more tricky because now the energy depends not just on one site, but what's happening on nearest neighbor sites and so on. But the procedure I've outlined, apart from the bigger matrices you have to deal with, and it's still manageable because it's just a pair of sites in this case. It's not you just turn the crank and do perturbation theory, and then you get a better variational estimate of where the phase boundary is.
Thanks.
Sure. Okay, that's been going on too long. All right, so thanks a lot, and please come to the discussion tomorrow morning if you didn't get enough at 9 a.m. Okay, see you later.
Thank you.
Thank you.
Thank you.